Welcome to this class. In the last class, in this module on reaction equilibria, we saw one of the fundamental relationships for reaction equilibrium, and that happens to be for an independent reaction the sum over I nu I, which is the stoichiometric coefficient, mu I, which is the chemical potential of that species I, the product of that and summed over all I, that equals 0. And we also said that if there are R independent reactions that occur in our system, then we will have one such equation for each of the R independent reactions, and therefore R such reactions will define that system at equilibrium. This is one of the very significant results, equation 614. It is very nice and compact, and it is good to remember this. This will automatically become a part of the memory. The recall is very easy for this equation. What we are going to do next is to look at phase rule for reacting biosystems, and the way we are going to do that is through some sort of an interactive method. We have already derived the phase rule for non-reacting systems in the previous module, and what I am going to do is give you some thoughts again on the background to that, and I will give you all the data and then let you come up with the phase rule for reacting biosystems, and I will give you time for that in this class. If you think about, or if we recall the phase rule equation 5.7, and that gave the number of degrees of freedom. In other words, the number of degrees of freedom is the number of independent variables that are required to complete the description of the system. We saw that the phase rule for the non-reacting system was f the number of degrees of freedom is c minus pi plus 2, c the number of components in each phase of the system, pi the number of phases. This was our equation 5.7 in the previous module. Let us recall that we arrived at the phase rule by considering the difference between the number of available variables and the number of independent equations between such variables. In the case of a system with reactions at equilibrium, the number of variables is the same, pi into c plus 1. There are no additional variables that are there, where, as mentioned earlier, pi is the number of phases and c is the number of components, and the number of independent equations between the variables is pi minus 1 equalities of temperature. Recall that T alpha equals T beta and so on. So if there are pi phases, you could consider that one composite equation as pi minus 1 equations or equalities of temperature. In a similar fashion, there were pi minus 1 equalities of pressure, that corresponds to equation 5.2, and pi minus 1 equalities or equations of chemical potential for each component, and we can write one for each component, and therefore the total number of such equalities of chemical potential is c into pi minus 1. So all this remains the same even for a system with reactions at equilibrium. The only additional thing is that for a reacting system with R independent reactions, we have R conditions of equilibrium of the form sum over I nu I mu I equals 0. I am going to leave you with this background. This is more than enough background to derive the phase rule for reacting biosystems. Please go ahead and do it. It can take about 15 minutes since you are doing it for the first time. It will give you a lot more confidence in the material itself. Go ahead and do it, and I will present the solution or the phase rule for reacting biosystems after about 15 minutes. Go ahead, please. Okay. So, we all know the background, the number of variables in the reacting system at equilibrium, the number of independent equations between the variables, all this the same as the case of the system without reactions. The only additional thing being these are conditions of equilibrium of the form sum over mu I equals 0. So, how did we go about deriving the phase rule earlier? We looked at the total number of available equations, which is pi minus 1 into C plus 2 as for the case without reactions, plus this R, and the number of variables minus the number of available equations, available independent equations between those variables actually gives us the degrees of freedom that we saw. Therefore, f, the number of degrees of freedom, is pi into C plus 1, the number of variables, minus the number of equations between them, independent equations between them. If we rearrange this, essentially some algebra, we would get C minus R minus pi plus 2. So, as you can realize, whatever was C earlier can be replaced by C minus R. So, C minus R minus pi plus 2, hopefully you got this in your own efforts, gives the number of degrees of freedom in a system with R reactions. Let us call this equation 615, and the, as can be seen, the number of degrees of freedom reduces by the number of reactions compared to a non-reacting system. Let us move forward. Now, let us look at equilibrium constants. I am sure you know what equilibrium constants are. You must have done this in your 11th standard, 12th standard chemistry, and probably in some other courses in the engineering discipline or in the biotechnology course before you took this course. So, you already know what equilibrium constants are. What I am going to give you here is a formalism from the fundamentals to get at equilibrium constants. So, you will know where it all rests on, and so it will be much easier for you to have an overall picture in terms of some fundamental thermodynamic quantities. To do that, let us first consider a perfect gas mixture, and as we saw in module 4, especially equation 4.1, the expression for chemical potential of species I in the case of a perfect gas mixture was mu I equals mu I naught plus RT ln Pi, which is the partial pressure of component I in the mixture. If we substitute equation 4.1 in equation 6.14, equation 6.14 is the condition for reaction equilibrium, sum over mu I equals 0. Now, we are going to substitute mu I with mu I naught plus RT ln Pi. If we do that, then we could write sum over mu I into mu I naught plus RT ln Pi equals 0. This is this condition here, which can of course be written as, we are just multiplying the terms and combining them appropriately using the definitions of log and the definitions of log of a to the power b and so on. We are going to do that now. So, if you do that, sum over I mu I naught plus RT is a constant here, T is a constant here, sum over I ln of Pi power nu I. If you recall, this would have been nu I ln Pi, which is ln of Pi power nu I. You can work this out by looking at the properties of the log function, and this is summed over all I, this equals 0. Or you can write this as nu I mu I naught sum over I equals minus RT, this is sum of log, which is nothing but log of the product that we all know, product of, as represented by this big pi here, product of Pi power nu I. Let us call this equation 616. and let us define this particular quantity product over I Pi power nu I, the stoichiometric coefficient, the partial pressure time raised to the power of the stoichiometric coefficient for each of the species involved as Kp. You would recall Kp, the equilibrium constant with respect to partial pressure, that essentially comes from this. So, product over I Pi power nu I is defined as Kp, equation 617, and therefore, we can write 616 as minus RT ln Kp equals sum over I nu I mu I naught. Therefore, we have a means of getting Kp in terms of the mu I naught values, the standard chemical potentials of I species multiplied by the appropriate stoichiometric constants and summed over all I would lead to minus RT ln Kp. Let us call this equation 618, and to illustrate the above, to get it in into familiar territory, since we are familiar with equilibrium constants from earlier courses, let us consider the reaction mixture given by equation 6.1, which is 2A plus B giving you 3C. Let us consider that for a minute to be a perfect gas mixture. In such a case, this is the equation 618 for this particular reaction can be written as minus RT ln Kp. What is ln Kp? The ln of the product of Pi par nu I. You know that nu I is positive for the products and negative for the reactants, and therefore, if you multiply that all together, it will be Pc cubed into Pa to the power of minus 2 into Pb to the power of minus 1, which can be written as Pc cubed divided by Pa squared Pb, and of course, the ln comes from here. This equals 3 mu c naught minus 2 mu a naught sum over I nu I mu I naught, 3 mu c naught minus 2 mu a naught minus mu b naught. We will call this equation 619. Therefore, this must be very familiar to you in terms of the equilibrium constant. How do you find that if given the partial pressures is like this, and you can relate it to the standard chemical potentials for that particular reaction. Let us stay with the perfect gas mixture for a little while longer, and as you can recall, there are many other equilibrium constants. The earlier one was based on partial pressure. You could have an equilibrium constant based on concentration, based on mole fraction, and so on, and they can be arrived at as follows. For the ith component, the partial pressure can be written as Ni by V RT. This is from the ideal gas equation, perfect gas mixture. So, mixture of ideal gases and so on. So, Ni by V RT is partial pressure, which Ni by V can be is nothing but the definition of the concentration, the molar concentration. Therefore, Ci RT. Let us call this equation 620 for in this context, and if we substitute equation 620 in equation 617, that will become very clear right now, and transposing, we will get Kp equals pi into Ci RT the whole power nu I. Can you do this bit of algebra right now? Just substitute 620 and 617 and get this expression. Take about 5 minutes to do that, and which can further be written as this. This is just the algebra part, the log and raising it to powers and so on. You need to get comfortable with this, so I will give you about 5 minutes to do this. Go ahead, please. Okay. You should have arrived at Kp equals product over I Ci RT the whole power nu I, which can of course be written as RT to the power of sum over nu I times the product of Ci power nu I. Let us call this equation 621. This is the definition of Kp, and if we call this as Kc, product over I Ci power nu I as Kc, then it is easy to see that Kc is nothing but Kp into RT raised to the power of minus sum over all the stoichiometric constants nu I. Let us call this equation 623. Just not this, there is probably one more. Let us recognize that Pi is nothing but P into Yi, equation 624, and let me leave you with this for another 10 minutes to derive Ky, the equilibrium constant based on the mole fractions Yi. Can you go ahead and do it on the same lines as we did for this? I will present the results after 10 minutes. Go ahead please. Okay. Now, taking Pi equals the total pressure times the mole fraction yi, and if we follow a similar exercise as above, write Kc in terms of, or Ky in terms of Kc and so on, you should get Ky is nothing but Kp into P raised to the power of minus sum over all nu I. Hopefully you got this in your own exercise, where our Kp is defined, or sorry, Ky is defined as product over I yi, the mole fraction, raised to the power of nu I, the stoichiometric coefficient. Let us call that equation 626. Now, all those equations that we derived so far, the equilibrium constants, were applicable for perfect gas mixtures. If the gas mixture is imperfect, which is usually the case, then the only change that we need to make, since we are working in terms of chemical potentials, is that the chemical potential needs to be expressed in terms of fugacities instead of partial pressures. This was given in equation 4.2. Chemical potential in terms of fugacities mu I equals mu I naught plus RT ln Fi hat. So, replace fugacities wherever there were partial pressures earlier, and if we do a similar exercise, I would leave this for you to do as a homework. So, if you do a similar exercise as for Kp, we should get minus RT ln Kf. Kf is the equilibrium constant based on fugacities, as equal to sum over I nu I mu I naught, where Kf, the equilibrium constant based on fugacity, is defined as product over I Fi hat raised to the power of nu I, that is our Kf. Let us call that equation 628. When we are almost out of time, when we meet in the next class, we will take things further. See you there.